Hey everyone, welcome back to Planetarian Daily. I'm Patrick in Vancouver and this is episode 39. Today we're looking at some genuinely fascinating work that spans from the deep evolutionary past to the frontiers of materials science and human well-being. What ties it all together is how life, at every scale, finds clever ways to persist through extreme conditions, whether that's a planetary catastrophe 100 million years ago or the daily grind of modern life. Let's dive in. First up is a story that gives us a much clearer picture of how some of the ocean's most intelligent animals made it through Earth's most devastating extinction event. Researchers have now sequenced the genomes of squid and cuttlefish and combined them with large global data sets. The picture that emerges is that these cephalopods originated in the deep ocean more than 100 million years ago. During the planet's largest mass extinction, the one that wiped out the dinosaurs and so many other groups, these animals didn't try to tough it out in the chaotic surface waters. Instead, they retreated to oxygen-rich deep-sea refuges where conditions were far more stable. What's striking is how remarkably conservative their evolution became once they settled into those deep environments. For millions of years, their body plans barely changed. They maintained a stable morphology while the world above went through dramatic upheaval. Then, once the extinction pressures eased, a post-extinction boom allowed them to diversify rapidly and move back into shallower habitats. The genomic evidence shows that the deep sea essentially acted as an evolutionary lifeboat, preserving a successful design that could later be deployed across many different ecological niches. I find this story quietly reassuring. It's a reminder that extreme environments don't always mean dead ends. Sometimes they function as protected workshops where life can ride out global crises and emerge later with its core toolkit intact. It makes you wonder what similar deep ocean refuges might still exist today, quietly preserving biodiversity that could prove crucial if our own climate keeps shifting rapidly. The strategy these cephalopods used, retreat, stabilize, then radiate, might hold lessons for how we think about conservation in an era of rapid change. While those ancient cephalopods were finding refuge in the deep, another mission is teaching us how the chemical building blocks of life can survive harsh conditions in space. Scientists have been carefully analyzing samples returned by NASA's OSIRIS-REx mission from the asteroid Bennu. What they're seeing is that organic compounds and certain minerals are clustered into 3 distinct region types on the asteroid. These patterns were shaped by uneven water activity in Bennu's distant past. Some areas experienced more aqueous alteration than others. The delicate organic molecules survived in very localized zones, protected by the specific chemistry around them. This patchy distribution tells us that the conditions capable of preserving complex chemistry weren't uniform across the asteroid. Instead, small differences in mineralogy and water exposure created safe pockets where prebiotic molecules could persist. It adds a layer of realism to our understanding of astrobiology. The early solar system wasn't a uniformly friendly chemical soup. It was heterogeneous, and that patchiness may have been exactly what allowed certain molecules to survive long enough to potentially seed life on planets like ours. This work is a beautiful example of how returning actual samples from space continues to reshape our assumptions. It's not just about finding organics, it's about understanding the very specific conditions that let them endure. That knowledge will help us interpret data from future missions to other asteroids, comets, and icy moons. Staying with animals that have mastered extreme environments, let's talk about one of the ocean's most recognizable predators. New biologging data on great hammerhead sharks shows they maintain peak hunting performance across wide seasonal temperature swings. Most cold-blooded predators slow down noticeably when water temperatures drop, but these sharks exhibit what's being called a thermal hustle. Their predatory efficiency stays remarkably stable between winter and summer months. This sets them apart from many other marine hunters who experience clear drops in performance when temperatures change. The data suggests the hammerheads have specialized physiological mechanisms that help maintain muscle function, sensory processing, and decision-making across a broad thermal range. It's an impressive adaptation for an animal that often travels long distances and encounters very different conditions throughout the year. I'm always struck by how much we still have to learn about the physiology of large marine animals. These findings don't just tell us about hammerheads, they highlight how varied the solutions to environmental variability can be. While some species are highly sensitive to temperature shifts, others have evolved ways to essentially buffer themselves. As our oceans continue to warm and become more variable, Understanding which species have this kind of thermal resilience could become increasingly important for predicting ecosystem shifts. From sharks that refuse to let temperature slow them down, we move to bacteria that might soon face a new point of vulnerability. Researchers at Université de Montréal have identified a previously unknown mechanism that bacteria use to remodel their cell walls during the critical moments of septum formation and daughter cell separation. This process allows the cells to divide successfully without bursting under the high internal pressure they generate. The discovery focuses specifically on the cleavage step that completes cell division. Because current antibiotics often target other parts of cell wall synthesis, this newly described mechanism represents a fresh target. Disrupting it could potentially stop bacteria from completing division while leaving human cells unaffected. It's the kind of basic mechanistic insight that often forms the foundation for entirely new classes of drugs down the road. This feels like classic incremental but important science. We're still discovering fundamental processes in organisms we've been studying for decades. Each new detail in the bacterial division playbook increases the chances we can design more precise interventions, especially important as antibiotic resistance continues to evolve. While we look for new ways to outsmart bacteria, engineers are building miniature tools that could transform how we measure our world. Applied physicists from Harvard and TU Wien have developed racetrack-shaped lasers on a microchip that produce bright and stable frequency combs. These tiny devices could bring laboratory-grade spectrometer precision to compact portable systems. One of the most promising applications is environmental gas analysis. Imagine being able to do high-precision air quality or greenhouse gas measurements with something that fits in your hand. The stability and brightness of these miniature combs is what makes the leap possible. It's another step in the long trend of moving sophisticated lab techniques out into the real world where they can be used more widely. Not the only small-scale breakthrough making headlines this week. Materials scientists at the University of Illinois Urbana-Champaign have created the first synthetic, highly conductive ferroelectric charged domain wall. They achieved this by carefully interfacing two different two-dimensional materials. The resulting structure shows remarkable versatility in its electronic and structural properties. This work points toward future applications in neuromorphic computing, systems that mimic the way brains process information, and in reconfigurable electronics that can adapt their function on the fly. It's exciting to see how stacking atomically thin materials continues to yield new phenomena that simply don't exist in conventional bulk materials. Shifting from materials that could power tomorrow's devices to something that touches on our daily sense of well-being, a multi-university study published in Nature Communications found that a person's position in the local income hierarchy predicts their well-being better than their actual earnings or even the size of income gaps in their area. In other words, how you stack up relative to the people immediately around you seems to matter more than the absolute numbers on your paycheck. What's encouraging is that strong civic and community life can substantially buffer the negative effects of sitting lower in that local hierarchy. The research highlights how much our immediate social context and daily comparisons shape our experience of life. It's a reminder that well-being isn't just about personal income, it's deeply relational and environmental. Speaking of resources we all depend on, 2 new papers have used Landsat satellite imagery to document both seasonal fluctuations and longer-term trends in water loss and gain across reservoirs worldwide. These datasets help fill important gaps in our ability to monitor these critical water bodies, which supply drinking water, generate power, and support irrigation for huge numbers of people. Understanding both the short-term ups and downs and the multi-year trends is becoming more urgent as climate patterns shift and demand grows. Satellite monitoring like this gives us a planetary-scale view that ground-based measurements alone could never provide. It's the kind of foundational data work that doesn't always make headlines, but will quietly inform water management decisions for decades to come. From mapping water on a global scale to fighting one of the most stubborn cancers at the cellular level, researchers have used lipid nanoparticles to target cancer-associated fibroblasts in the dense protective matrix that surrounds pancreatic tumors. By weakening this desmoplastic barrier, the approach also reduces immune suppression within the tumor environment. The result is significantly improved effectiveness of CAR T-cell therapy against pancreatic ductal adenocarcinoma. This notoriously difficult cancer has resisted most immune-based treatments for years, largely because of that dense stromal barrier. Finding a way to loosen it without broadly damaging healthy tissue is a meaningful step. It's not a cure on its own, but it suggests that combination strategies attacking both the tumor cells and their protective microenvironment could make previously resistant cancers more treatable. Another clever immune engineering approach comes from researchers who modified natural killer cells and T cells with metabolite sensing receptors. The modification helps these immune cells better infiltrate tumors in mouse models and improves overall treatment outcomes. The strategy takes advantage of the unique metabolic signature of the tumor microenvironment, essentially giving the immune cells a chemical nose for finding the cancer. While those cells are being rewired to fight disease, another team has built a material that speaks the language of both electronics and living tissue. Researchers in Dresden have developed a soft, electrically conductive, and biologically active hydrogel that integrates seamlessly with living tissue. The material allows precise control of both electrical and biochemical signals at the interface between synthetic devices and biological systems. This kind of bioelectronics work is gradually closing the gap between our rigid electronic devices and the soft, wet, dynamic environment of the body. The better that interface becomes, the more possibilities open up for treating neurological conditions, monitoring chronic disease, and even augmenting healthy function. From lab-made materials that interface with the body to a surprisingly simple intervention that improves the environment inside our homes, a Finnish study found that simply placing forest soil on entryway doormats significantly reduced human-associated bacteria indoors. The intervention shifted the indoor microbiome closer to outdoor profiles, which could promote healthier microbial environments, especially in urban settings where people spend most of their time disconnected from nature. It's one of those low-tech findings that feels almost too straightforward to be true, yet the data support it. Our modern obsession with sterility might be coming at a cost to the diversity of microbes we're exposed to. Bringing a little bit of the forest inside, literally, may be a practical way to restore some of that lost connection. Now, here's something most of us get wrong when we think about the differences we see between men and women in work, health, and life outcomes. Many assume those gaps come down mainly to pay differences or overt bias. The reality is often more immediate and physiological. Women frequently carry a heavier invisible load of unpaid time obligations, household coordination, emotional labor, family logistics, that literally leaves them with fewer hours of discretionary time. That hidden time gap doesn't just affect career progression. It shapes sleep, stress recovery, and the consistent blocks of unallocated time that our brains and bodies need to function at their best. Executive function, physical resilience, immune response, all of these are sensitive to how much truly free time we have. Small daily differences compound over years into measurable gaps in cognitive performance and long-term health markers. The practical takeaway is to treat time allocation with the same seriousness we give nutrition or exercise. Tracking your actual hours of uncommitted time each week can reveal surprising leverage points for protecting recovery and performance. It's not about doing less overall, it's about protecting the white space that lets everything else work better. There's developing research looking at how these time use patterns connect to longevity markers, and I suspect future studies will continue to strengthen the case for rethinking both workplace policies and personal habits. It feels like an area where relatively small cultural shifts could have outsized effects on health and equity. That's Planetarian Daily for today. We covered everything from ancient squid surviving mass extinctions to new ways of fighting pancreatic cancer and rethinking how we value our time. If you enjoyed the episode, a rating or review on Apple Podcasts or Spotify really does help new listeners discover the show. I'm Patrick in Vancouver. Thanks for spending part of your day with me, and I'll talk to you again tomorrow. This podcast is curated by Patrick, but generated using AI voice synthesis of my voice using ElevenLabs. The primary reason to do this is I unfortunately don't have the time to be consistent with generating all the content, and wanted to focus on creating consistent and regular episodes for all the themes that I enjoy, and I hope others do as well.